All right, in this section, we're going to talk about section 4.4 dealing with exponential and logarithmic equations. So here we're going to be solving two types of equations, exponential and logarithmic equations. And in this section, we're going to be using like basis to solve exponential equations and use logarithms to solve exponential equations. And then we're going to be using the definition of a logarithm to solve logarithmic equations and use the one-to-one property of logarithms to solve logarithmic equations. Okay, so let's talk about what an exponential equation is. It is an equation containing a variable in an exponent. So here's some examples here. 2 to the 3x minus 8 is equal to 16 is an exponential equation because that exponent does have a variable in it. Also, 4 to the x is equal to 15. That too is an exponential equation. The exponent is just x, and then 40e to the 0.06x equals 240. That too is an exponential equation because of the x in the exponent for the base of e. Now these are going to be the types of exponential equations that we will be solving. And there are two ways of solving an exponential equation. One of them is solving exponential equations by expressing each side as a power of the same base. So we use this particular rule. If b to the m is equal to b to the n, then m is equal to n. That means if your bases are the same, we can set our exponents to be equal to each other. Okay. So to solve an exponential equation, when you express each side as a power of the same base, we have to rewrite the equation in the form of b to the m equaling to b to the n. Because you want the bases on both sides of the equation to be the same. Once they're the same, we can set our exponents equal to each other. That means we set m equal to n. That's step number 2. And then step number 3 is to solve for the variable. Okay. So now let's look at a couple of examples of this by expressing each side as a power of the same base with our exponential equations here. So in example 1, we're going to solve, and we're going to start with part A, where we got 5 to the 3x minus 6 is equal to 125. 5 to the 3x minus 6 is equal to 125. Well, notice on the left side, the 5 is simplified as far as we can get it to be simplified. So I'll just write 5 to the 3x minus 6. But that 125, I know that's a multiple of 5. So what I'm going to do there is write 125 with a base of 5 by dividing 5 into 125. And I'm going to keep dividing by 5. So 5 into 125 will go 25 times evenly. And then 5 goes into 25 5 times. And then 5 goes into itself 1 time. So you can see here that your 5 is used as a factor 3 times. So in this case here, 125 can be written as 5 to the 3rd power. So I got 5 to the 3x minus 6 is equal to 5 to the 3rd. Well, my bases are the same. That means I can set this exponent to be equal to that exponent. So I can set 3x minus 6 to be equal to 3. Here I'm setting my exponents to be equal to each other. And then we're going to solve this equation for x. So to get 3x by itself, I need to add 6 to both sides. So that means I'm going to have 3x is equal to 9. And then to solve for x, I'm going to divide both sides by 3. So that means x is equal to 3. Now, if you like, you can do the check by replacing the x in the original equation with that 3. So if I do 3 times 3, that would be 9. 9 minus 6 would be 3. And then 5 to the third power would be 125. So here x equals 3 is the solution to that exponential equation. Okay, now look at part B. We got 8 to the x plus 2 equals 4 to the x minus 3. Well, I can't write 8 as 4 to some power that would give me 8. But I can find a number that's common in 8 and 4. And in this case, it's going to be 2. So I can write 8 with a base of 2 and 4 with a base of 2. Because in this case here, okay, I might need to write this over here to this side. 8 is equivalent to this, 2 times 2 times 2, or 2 to the third. And then 4 is 2 times 2, or 2 squared. So in this case here, I'm going to write this with a base of 2. So this will be, in this case, 2. 8 will be 2 to the third. And that's raised to the power of x plus 2. And that's equal to, that 4 will be 2 squared. Oops. This will be 2 squared in parentheses. And that's going to be to the x minus 3. Okay. Now there's a rule that says if you raise a power to a power, you can multiply your exponent. So I'm going to write this as 2 to the 3 times in parentheses x plus 2. And then I'm going to do the same thing here, multiply the exponents for the base of 2. So this will be 2 to the 2 times the quantity x minus 3. Now as you can see here, the bases are the same. So here I can go ahead and set my exponents equal to each other. So I can set that 3 times the quantity x plus 2 to be equal to 2 times the quantity x minus 3. And then I'm going to use the distributive property on both sides of this equation. So distribute the 3 over the x plus 2, you're going to get 3x plus 6. And that's equal to, on the right side, distribute the 2 over the x minus 3. This will be 2x minus 6. So I got 3x plus 6 equal to 2x minus 6. And then we'll go ahead and solve this equation for x by moving the 2x over to where the 3x is. I need to subtract 2x on both sides. So 3x minus 2x will be 1x, or just x plus 6 equal negative 6. You'll want to forget this negative sign that's in front of the 6, or the minus sign. So to solve for x, I'm adding 6. I need to subtract 6 on both sides. That would mean x will be equal to negative 6 minus 6 will be negative 12. So here, x will be equal to negative 12. Okay. So that's how you solve an exponential equation when you want to express each side as a power of the same base. Now the second method comes in when you're not able to express each side as a power of the same base. Here we're going to be using logarithms to solve exponential equations. Okay. Kind of have to tilt the paper so that you can see this procedure here. Okay. All right. There are 4 steps for solving an exponential equation using logarithms. The first step is to isolate the exponential expression, meaning that you're going to have to move terms over to to the other side in order to get that exponential expression by itself. And then number 2, take the natural logarithm on both sides of the equation. And that's for all exponential expressions other than the ones that have a base of 10. Okay, now if you have a base of 10, you have to take the common logarithm on both sides of the equation for base 10. And then number 3, you're going to simplify using one of the following properties. And that is, either you're going to have to use the fact that ln of b raised to the x will be equal to x times ln of b. That's using the power rule by bringing the exponent in front of the natural logarithm. Or you might have to use the inverse property of ln of e to the x equals to x. That means ln of e to whatever your exponent is that exponent. Or the log of 10 to whatever your exponent is that exponent. And then the final step would be to solve for the variable. Okay. So we're going to use that procedure with these examples here. So here we're going to find the solution set and then use a calculator to obtain a decimal approximation to 2 decimal places for the solution. So we're going to start with part A. And that's going to be this. 5 raised to the x is equal to 134. Well, already you see the exponential part is by itself. That expression 5 to the x is already by itself, so we don't need to move terms over to the other side. Now, it's not a base of 10, so we don't need to take the common logarithm on both sides. We will have to take, in this case, the natural logarithm on both sides. So we're going to have ln of 5 to the x equals ln of 134. Now on the left side, we're going to have to use the power rule by bringing the exponent in front of the natural log of 5. So this x will be in front, and then ln of 5 equals ln of 134. And now we're going to solve this equation for x. So here, x is multiplied by ln of 5, so we need to divide both sides by ln of 5. So that means x is equal to ln of 134 divided by ln of 5. This represents the exact value Now, I think in the homework on My Math Lab, they want the exact value, and then they want the approximate value. So to get the approximate value, you have to use your calculator to calculate ln of 134 divided by ln of 5. So the first thing I do is press the ln key. If you remember, ln is the key that's on the left side of number 4. So you press that ln button. It'll give you the left parentheses, and then 134, and then you have to close the parentheses because you only want the natural logarithm of 134. And whatever that is, it will be divided by ln, press the ln key, and then 5, close parentheses. Now we're going to give a decimal approximation to 2 decimal places. So here, to 2 decimal places, this will be approximately 3.04. So the approximate value of x will be 3.04. Okay. All right, next is part B, 10 to the x equals to 8,000. 10 to the x equals 8,000. Well, already the 10 to the x, that's the exponential expression, is by itself already. But notice we have a base of 10. So instead of taking the natural log on both sides, it would be much easier to take the common logarithm on both sides. So I'm going to do log of 10 to the x, and that's going to be equal to log of 8,000. Because it's a base of 10, I'm just taking the common logarithm on both sides instead of the natural logarithm. Now, there is a property that says here, if you have the log of 10 to whatever your exponent is, it's going to be that exponent. So log of 10 raised to the x will simply be x. And then that's equal to the log of 8,000. Now, already we have our exact value. Okay, and I apologize for writing off the screen, but I'm not able to get everything that I want to on here. So what I just wrote is exact value. Now, to get the approximate value, we just type in the log of 8,000. So we press the log button for the log, which is on the left side of number 7. So log is there. And then left parentheses is already there. Type in 8,000 and close your parentheses and hit enter. So the 2 decimal places, this will be approximately 3.90. So in this case here, the approximate value for that particular logarithmic equation would be 3.90. Okay. That's the solution for that logarithmic exponential equation. Exponential equation. Okay. Let's say we had something like this. Here I want to solve 7e to the 2x minus 5 equals to 58. And I want to find the solution set and then use a calculator to obtain a decimal approximation to 2 decimal places for this solution. So I'm going to go ahead and write down the equation 7e to the 2x minus 5 equals 58. So here we need to get that e to the 2x by itself. Meaning I need to move the 5 over to the other side and get rid of the 7 that's in front of it. Let's start by getting rid of the minus 5. We're subtracting 5, so that means I need to add 5 to both sides of this equation. So here's 7e to the 2x will be equal to 63. And then get e to the 2x by itself. It's being multiplied by 7, so I need to divide both sides by 7. So that means e to the 2x is equal to 63. No, 63 divided by 7, that's going to be 9. So e to the 2x will be equal to 9. And then I know this. E and the natural log are inverses of each other. So with that, I will take the natural logarithm on both sides. So I have ln of e to the 2x, and that's equal to ln of 9. And I know this. If I have ln of e to whatever my exponent is, it's going to be that exponent. So ln of e to the 2x is 2x. And that's going to be equal to the natural logarithm of 9. And then divide both sides by 2. This will be x is equal to ln of 9 divided by 2. Now that is your exact value. Now for the approximate value of x, this is where we use our calculator to do that. And you can forgive me for putting this in front of what I just wrote. So here we're going to press the LN key and then type in 9. We need to close the parentheses around the 9 because we only want the natural logarithm of 9. And then that's going to be divided by 2. So the 2 decimal places, this will be about 1.10 because the second digit after the decimal point is a 9. Behind it is an 8. That 8 will increase the 0.09 to 0.10. So it'll be 1.10. Okay. Okay. Let's look at one more of these. And this one is going to be a little bit more complicated here. Here we got 3 to the 2x minus 1 equals 7 to the x minus 1. And we're going to find the solutions and then use a calculator to obtain a decimal approximation to 2 decimal places for the solution. Okay. So I'm going to go ahead and rewrite this. Let's see. 3 to the 2x minus 1 equals 7 to the x plus 1. Now notice that the exponential expressions are by themselves on the left side and on the right side. So those bases are not base 10, so I'm not going to take the logarithm. I can go ahead and take the natural logarithm on both sides. So I'm going to do ln of 3 to the 2x minus 1. That's equal to ln of 7 to the x plus 1. And then I'm going to use the power rule for logarithms by pulling the exponent in front of the natural logarithm. So this 2x minus 1 will be in front of ln of 3. And it's going to be in parentheses. So 2x minus 1 in parentheses, that'll be multiplied by ln of 3. And the same thing here, I'm going to pull the x plus 1 in front of the natural logarithm. And that's going to be in parentheses as well. So it'll be x plus 1 in parentheses times ln of 7. Now the next step, on each side of the equation, I'm going to use the distributive property. So I'm going to distribute the ln of 3 over the 2x minus 1. So ln of 3 times 2x, I'm going to write that as 2x times ln of 3. And then minus ln of 3 times 1 will be ln of 3. And then that's equal to the x plus 1 will be, well, I'm going to distribute the ln of 7 over the x plus 1. So ln of 7 times x will be x times ln of 7. And then plus ln of 7 times 1 will be ln of 7. Okay. Now here's what I'm going to do here in this next step. I'm going to move all the terms that have an x in the natural log expression and move all the other terms on the other side. So the ones that have an x, I'm going to move those over to the left-hand side. So I know I got that 2x times ln of 3. I'm going to keep that there. But I'm going to move that x ln of 7 to the other side. When I do that, it's plus, but when I move it over to the other side, it will become minus x times ln of 7. And then that's equal to, well, I've already got ln of 7 on the right side. Now that minus ln of 3, when I move that over to the other side, it will be plus ln of 3. So what I'm doing here is getting all the terms that have an x in it on the left side. And the ones that don't have an x in it, I'm moving over to the other side. So now on this side, where I got 2x ln of 3, minus x ln of 7, they both have a common factor of x. So I can factor out the x. And what's going to be left is 2x divided by ln, 2x ln of 3 divided by x would be 2 ln of 3 minus x ln of 7 divided by x would just be minus ln of 7. And that's equal to ln of 7 plus ln of 3. And now we can solve this equation for x because x is multiplied by 2 ln of 3 minus ln of 7. So I'm going to divide both sides of that equation by 2 ln of 3 minus ln of 7 on both sides. So this x will be by itself. So x will be equal to ln of 7 plus ln of 3, all divided by 2 ln of 3 minus ln of 7. Now this is the exact value of that exponential equation. So now to find the approximate value, this is where I use my graphing calculator. And I'm going to tell you this, if you're going to use your graphing calculator, I would suggest putting the numerator in parentheses and the denominator in parentheses, as you're going to see here. So let's use our calculator and get our approximate value here. The numerator is ln of 7 plus ln of 3. So left parentheses, press the ln key, and then 7, then close the parentheses, and then plus, press your ln key again, and then 3, close parentheses. And then you got to close it again because we opened the left parentheses on the left side to begin with. That will be divided by, and then the denominator will be in parentheses. So left parentheses. For 2 ln of 3, we type in 2, press the ln key, and then 3, close parentheses. And then minus, press the ln key, and then 7, close the parentheses. And then you want to close it again, because that denominator started off with the left parentheses. And then press enter. Now we want that to 2 decimal places, so this will be approximately 12.11. So the approximate value of x will be 12.11. Okay. All right, next we're going to look at logarithmic equations. Okay. I apologize for not having this focusing too close. A logarithmic equation is an equation containing a variable in a logarithmic expression. And these are examples of logarithmic equations here. Like log to the base 4 of x plus 3 is equal to 2. And also the natural log of x plus 2 minus the natural log of 4x plus 3 is equal to the natural log of 1 divided by x. That's an exponential equation. The one on the left has the logarithm on one side. The one on the right has the natural log on both sides of the equation. We're going to be dealing with those as well. So now, how do we solve a logarithmic equation? Using the definition of a logarithm. That's going to be one of the two methods of solving logarithmic equations here. Number one, you want to express the equation in the form of log to the base b of m equal to c. And then number two, you want to use the definition of a logarithm to rewrite the equation in exponential form. Now, back in section 4.2, we did talk about converting from logarithmic form to exponential form. You start with the subscript, which is your b, the c, that's after the equal sign, that's your exponent for the b, and that's equal to whatever is immediately after the logarithm. So log to the base b of m equal to c would mean b to the power of c equals m. And then next you're going to solve for the variable. And then number 4, you're going to check your proposed solutions in the original equation. This step is very important because you want to include in the solution set only values for which your m is greater than 0, because we cannot take the logarithm of a negative number, nor can we take the log of 0. Okay, so now let's take a look at these two examples here. So in part A, I got log to the base 2 of 4 equals to 3. Log to the base 2 of 4 equaling to 3. And I want to solve this using logarithms. Notice that the logarithmic expression is by itself is already in the form of log to the base b of m equals to c. So we can write this in its equivalent exponential form. So that means I'm going to be using that study tip that was given to you back in section 4.2. Start with the subscript, which is your 2. The 3 will be the exponent for 2. That's going to be equal to this x minus 4. So here, log to the base 2 of x minus 4 equaling to 3 in its equivalent exponential form will be 2 to the third. And that's equal to that x minus 4. And then I'm going to solve this equation for x. Well, 2 to the third is 2 times 2 times 2, which is 8. So I'm going to have 8 is equal to x minus 4. And then to solve for x, we're going to add 4 to both sides. So that means x then will be equal to 12. Now keep in mind that is my proposed solution, but to see that satisfies the logarithmic equation, I need to do the check by replacing the x with 4 in that equation. So here's the check. I'm just going to go ahead and substitute this x in this equation with the 12. So I'm going to have log to the base 2 of 12 minus 4. I want to know if that's going to be equal to 3. Well, 12 minus 4 would be 8. So log to the base 2 of 8 is equal to 3. And then I can write this in its equivalent exponential form by doing this. 2 to the third should equal to 8. And if I do 2 to the third power, that would give me 8, which does equal to 8. So that checks. So that means x equal 12 is the solution to that logarithmic equation. Okay. All right, now part B, we got 4 times the natural log of 3x is equal to 8. Okay. Now, you're going to need to remember back in section 4.2 when we were talking about natural logarithms. Well, if you have ln of x, that can be written as log to the base e of x, because that's what natural logarithms are, log to the base e. So in this case here, I'm going to rewrite that as 4 times the natural log to the base e of 3x equals 8. I'm just writing it in a different way. I'm just writing it with a log in it, because log to the base e of x is the same as the natural logarithm of x. So now, first thing you need to do is get rid of the 4 that's in front of log to the base e of 3x by dividing both sides by 4. So here, log to the base e of 3x equals 2. And now I can write this in its equivalent exponential form. So here, log to the base e of 3x equals to 2 starts off like this. E to the second, or e squared, is equal to the 3x. So I'm applying that study tip that I talked about back in section 4.2, converting from from logarithmic to exponential form. Now I want to solve for x. X is being multiplied by 3, so I need to divide both sides by 3. So here x is equal to e squared over 3. Now that, of course, is my proposed solution. So now I need to do the check to see if this satisfies the original equation. And I'm going to replace the x with e squared over 3. So this will be 4 times ln of 3 times e squared over 3. That should equal to 8. Now when I simplify this, these 3's divide out. So now you're going to have 4 ln of e squared equals to 8. Now I'm going to bring down the 4. Now when I do ln of e squared, ln of e to whatever my exponent is that exponent. So ln of e squared would be 2. So I want to see if 4 times 2 equals 8, and it does. 8 does equal to 8. So that e squared over 3 is the solution to that logarithmic equation. Okay. All right, now, next thing I need to talk about is what's very important here. It is important that you always check your proposed solutions of the logarithmic equation in the original equation. And you want to exclude from the solution set any proposed solution that produces the logarithm of a negative number or the logarithm of 0. Because we know we can't take the log of 0, and we cannot take the logarithm of a negative number. Like in this example, not only are we going to solve, we're going to do the check. We got the log of x plus the log of x minus 3 equals 1. Okay, so now the first thing we need to do here is condense as a single logarithm. That means we need to use either the product rule or the quotient rule or the power rule that was talked about in section 4.3. Notice we have a plus sign in between the two logarithms. So that means we got the log of the sum of their individual logarithms. We can condense that as the log of the product. So I'm going to write this as the log of x times the quantity x minus 3. And that's equal to 1. Okay. Now, if you need a refresher on condensing logarithms, what I would suggest is watch the video for section 4.3 for properties of logarithms, where we talk about how to condense using the product rule, the quotient rule, and the power rule. Okay, now we got a log on one side. That means I need to write this in its equivalent exponential form. However, there's no subscript for the log, but that's understood to be 10. Anytime you don't have a subscript for the logarithm, it is understood to be 10. So this is log to the base 10 of x times the quantity x minus 3 equaling to 1. Writing this in exponential form, this will be 10 to the first power. And that's equal to that quantity, x times x minus 3 in parentheses. And now we're going to simplify all of this. So here, 10 to the first power is 10, and that's equal to x times x minus 3. If you distribute the x over the x minus 3, you'll get x squared minus 3x. Now we have a quadratic equation. But first we need to get a 0 on one side of that quadratic equation. And I need to do that by moving the 10 over to where that x squared minus 3x is. Subtract 10 on both sides. So that means I'm going to have a 0 on this side equal to x squared minus 3x minus 10. Now, here I can factor x squared minus 3x minus 10 into two binomials here. That x squared will be broken up as x and x. And then the factors of 10 that would give me negative 3x as a middle term will have to be 5 and 2. But since the middle term is minus, the larger of the two factors will have to take the sign of that middle term. So that 5 has to be minus and the 2 has to be plus. So here I get x minus 5 times x plus 2 equal to 0. And then we set each binomial factor equal to 0. So x minus 5 times x plus 2 equal to 0 means x minus 5 equal to 0, or x plus 2 equals 0. And then we solve each equation for x. So for the x minus 5 equal to 0, if you add 5 to both sides, you'll get x is equal to 5. Or for the x plus 2 is equal to 0. If we subtract 2 on both sides, you'll get x is equal to negative 2. Now, those are my two proposed solutions. I need to do the check to determine which one of these will satisfy the original equation. So, let's start with the check for x equal 5. So I'm going to replace each x here with 5. So this will be the log of 5 plus the log of 5 minus 2. 5 minus 3 equal to 1. That's a 3. So here, log of 5 plus log of 5 minus 3 is going to be 2. That should be equal to 1. Now on the left side, I have the sum of their individual logarithms. I can condense that as the log of the product. So log of 5 plus the log of 2 would be the log of 5 times 2. That should equal 1. Well, if I multiply 5 times 2, that's going to be 10. So log of 10 equals 1. Now you can do this in the calculator. Press the log key and then 10. Log of 10, that's understood to be a 1, which does equal to 1. So I know x equals 5 is a solution to that logarithmic equation. Now, I also got to do the check for x is equal to 2. Negative 2. We're going to substitute each x with negative 2. So I'm going to have the log of negative 2 plus the log of x, again, negative 2 minus 3 equals to 1. And I can do negative 2 minus 3, which will give me negative 5. So I'm going to bring this down. But here, I got a problem. I got the log of a negative number. I cannot take the log of negative 2, and I cannot take the log of negative 5. So I can't take the log of a negative number. That is undefined. So we need to exclude x equal -2. So the only solution for that logarithmic equation would be x is equal to 5. Okay. So that's how we use the definition of a logarithm to solve logarithmic equations in this case. Now let's say we have the logarithm on both sides of the equation. So here we need to use something called the one-to-one property. So we're going to solve logarithmic equations using the one-to-one property. And there are 4 steps. Number 1, you want to express the equation in the form of log to the base b of m equaling to log to the base b of n. And then use the one-to-one property, which is going to be this. If log to the base b of m equals log to the base b of n, then what's after the logarithm we can set equal to each other. M equals to n. And then next is to solve for the variable. And then number 4, it is a logarithmic equation. You have to check your proposed solutions in the original equation. And your solution set would be those values where m is greater than 0 and n is greater than 0. We know we cannot take the log of a negative number, nor can we take the log of 0. In that first statement, where you have to express the equation in the form of log to the base b of m equaling to log to the base b of n, that's because in this case you have to use either the product rule or the quotient rule or the power rule to do that. Okay, take a look at example 7. Here I got log of x plus 11, and that's equal to the log of x plus the log of 11. So here I'm going to solve, and I have to do the check here as well. Now notice the left side is a single logarithm. So I'll go ahead and write down the log of x plus 11. But the right side, I got a plus sign in between the logarithms. That tells me I have the log of the product. So I need to condense that. The sum of their individual logarithms, which will be condensed as the log of the product. So log of x plus log of 11 would be the log of, I'm going to put the 11 in front of the x. So it'll be log of 11 times x. Okay. Now this I can use the one-to-one property. Okay. Because I got log to the base 10 on the left side and log to the base 10 on the right side. They're both the same. So I can set this expression of x plus 11 to be equal to 11x. So now I can solve this equation for x by subtracting x on both sides. So that means 11 is equal to 11x minus 1x, that would be 10x. So 11 is equal to 10x. Then divide both sides by 10. They might want that as a fraction 11/10. But for the sake of checking that proposed solution, if I do 11 divided by 10, this will be equal to 1.1. And I'm going to use that 1.1 when I do the check of this proposed solution. So I'm going to check x equal to 1.1 by substituting each x in that equation with 1.1. So here I got the log of 1.1 plus 11. That's equal to the log of 1.1 plus log of 11. Now, if I add 1.1 to the 11, that's going to be 12.1. So this will be the log of 12.1. And that's equal to, and I'm going to condense using the product rule. The sum of their logarithms is condensed as the log of the product. So this will be the log of 1.1 times 11. So the left side is log of 12.1, and that's equal to the log of, multiply 1.1 times 11, and you'll get 12.1. And this checks because the left side and the right side are exactly the same. So we're going to say x is equal to 11/10. That will be the solution to that logarithmic equation. Okay, now look at part B of example 7. Here we got the log of the quantity x plus 10 minus the log of 2 is equal to the log of 4x plus 1. Now notice on the left side I have the minus sign in between the logarithms. That means I have the difference of their logarithms. That can be condensed as the log of the quotient. So log of x plus 10 minus log of 2 will be this. The log of the x plus 10 goes in the numerator. That 2 would be in your denominator. So I got the log of x plus 10 divided by 2. And then that's going to be equal to the log of 4x plus 1. That right there is a single logarithm on the right side. Now, notice that I have the log to the base 10 on both sides. They're both equal, so I can set this expression to be equal to that expression using the one-to-one property. So this would be x plus 10 divided by 2 equals 4x plus 1. And you know what I'm going to do with that 4x plus 1? I'm going to put that over 1 and then cross multiply. So here, x plus 10 times 1 would be x plus 10. And then that's going to be equal to 2 times the quantity 4x plus 1. That's 2 times that 4x plus 1 is that expression. Now I'm going to distribute the 2 over the 4x plus 1. So here, x plus 10 equals 2 times that 4x is 8x plus 2 times 1. That will be 2. And now we're going to solve for x by getting all the variables on one side of this equation. It'll be easier to move the x over to where the 8x is by subtracting x on both sides. So that means I got 10 is equal to 8x minus 1x, that's 7x plus 2. And now to get that 7x by itself, I'm adding 2, so I need to subtract 2. So that means 7x is equal to 8. And then finally divide by 7. I'm going to leave that as a fraction. X equals 8 over 7. So that's my proposed solution for that logarithmic equation. Now, of course, we need to do the check. So I'm going to check x equals 8 over 7. I'm going to show you how to use the calculator for this, for fractions. We're going to substitute each x with 8 over 7. So this will be the log of 8/7 plus 10 minus the log of 2 is equal to the log of 4 times 8/7 plus 1. Okay, now I'm going to have the log of in the left side. I'm going to show you how to do 8/7 plus 10 in the calculator. Here we go. I'm going to type in 8 and then divide it by 7. and then plus 10. Now, there is a button that says Math. That's this button right here on the left side. Press that Math key, and then select number 1 for fraction. It will convert your answer to a fraction. So 8 divided by 7 plus 10 as a fraction will be 78 over 7. And then minus the log of 2 is equal to the log of. Now for that 4 times 8, 7 plus 1, I'm going to do 4, and then left parentheses, 8 divided by 7, and then I'm going to close the parentheses, plus 1. And then press that Math button, and then select number 1 for fraction. That's going to give me 39/7. So 4 times 8 divided by 7 plus 1 will be 39/7. Now notice on the left side I have the difference of their logarithms. I need to condense that as the log of the quotient. So this will end up being the log of. The numerator is 78 over 7, and the denominator will be 2. And that should equal to the log of 39/7. Now if I do 78 divided by 7 and then divided by 2 on the calculator, here we go, 78 divided by 7, close parentheses, and then divide by 2. Then press this Math key, and then select number 1 for fraction. Guess what? I get 39/7. So here, this is the log of 39 over 7, and that does equal to the log of 39 over 7. So this checks. So here, x equal 8 over 7 is the solution to that logarithmic equation. Okay. So with your logarithmic equations, you must do the check. Okay. All right, next, we'll talk about, well, we're going to revisit those compound interest formulas that we talked about back in section 4.1. So here we can use compound interest. We can use the compound interest formulas to determine the amount of time required for an investment to reach a certain amount at a specific interest rate, or we can find the annual interest rate of an investment. And if you recall, these are the formulas that we used. If you have n number of compounders, whether it's compounded semi-annually, quarterly, monthly, or daily, we use that first formula, A is equal to P times the quantity 1 plus R divided by N raised to the N times T. And only for continuous compounding, we use the formula A is equal to P times E to the RT. So that's very important there. Okay, now let's look at example 8. How long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? All right, so let's identify what we already have. We have a P, which is going to be the principal or the amount of the investment. That's $1,000. We want it to grow to $3,600. That's going to be the A. And the interest rate is 8%. Now, 8% has to be written in a decimal form by doing 8 divided by 100, which will give you 0.08. And it's compounded quarterly, so your N, if you recall, equals 4. Now, if we have n number of compoundings, we have to use this formula right here. A is equal to I'll go and write it down here. A is equal to P times the quantity 1 plus R divided by N. That's raised to the N times T power. Now, we're finding out what T is. So we just substitute what we already know in that formula. So that A is the 3600 that goes here. And that's equal to the P, which is 1,000, times the quantity 1 plus R is in decimal form your interest rate 0.08 divided by N, which is 4. That's raised to the N, which is 4, and T is what we're trying to find. So your exponent there will be 4 times T. Now let's simplify all of this, especially what's in the parentheses here. That 3600 is equal to, bring down the 1000. Now if I do in the calculator 1 plus 0.08 divided by 4, I'm going to get 1.02. So this is 1.02 to the 4t power. Now here I got an exponential equation. I need to get the exponential part by itself. That 1.02 to the 4t. I'm multiplying it by 1,000. So I need to divide both sides by 1,000. So 3,600 divided by 1,000 would be 3.6. And that's equal to these 1,000s divide out. I'll be left with 1.02 to the 4t power. So here I have the exponential part by itself. Now what I need to do here, since that base is not base 10, I can take the natural logarithm on both sides of this equation. So I'm going to take the ln of 3.6 on this side and the ln of 1.02 to the 4t on that side. Here I'm taking the natural logarithm on both sides. Now on the right side of this equation, I'm going to use the power rule by bringing the 4t in front of the ln. So I get ln of 3.6, and that's equal to, I'm going to pull the 4t in front. That'll be multiplied by ln of 1.02. And now I can solve this equation for t. T is being multiplied by 4 and by ln of 1.02. So I'm going to divide both sides by 4 ln of 1.02. So now I'm going to have t by itself. Because the 4's are gone, ln of 1.02, they're gone. Now here's the exact value, but here I need to get a approximate value to the nearest tenth. So let's see. I'm going to do ln of 3.6 and close the parentheses, divided by, and I'm going to put the denominator in parentheses as well. This will be 4, and then I'm going to press the ln key, and then 1.02. I'm going to close the parentheses for the ln, and then close the parentheses again for this left parentheses here that I entered. And let's see if I press enter. Now this is going to be to 1 decimal place. So 16.171 to 1 decimal place would be approximately 16.2. So in this case, it's going to take 16.2 years, because the time is going to be in years, for a $1,000 investment to grow to $3,600 at 8% compounded quarterly. Okay? Because it was compounded quarterly, I had to use that formula there. And in this case, we were finding the time. Okay, now the final example. number 10. Well, number 9. Got a couple of examples here. How long will it take for an $8,000 investment to double at an interest rate of 8% compounded continuously? And here I want to round the answer to one decimal place. So in this case here, we have an $8,000 investment. That will be P. The interest rate is 8%. Now 8% again is a decimal. You can do 8 divided by 100, you'll get 0.08. This time it's compounded continuously. So this will be the compound interest formula that we have to use here. A is equal to P times e to the RT. Because it says compounded continuously. That's the formula we have to use. And it says we want to double it. We want the investment to double. So if we double $8,000, that will mean A will have to be $16,000 because we want the investment to double. So in this case here, your A will be 16,000 equals to P, that's 8,000, times e to the r, that's going to be 0.08 times t. So now we want to get the exponential part by itself, that e to the 0.08t by itself. We're multiplying it by 8,000, so we need to divide both sides by 8,000. So 16,000 divided by 8,000 will end up being 2, and that's going to be equal to e to the 0.08t. And of course, e and ln are inverses of each other, so I need to take the natural logarithm on both sides. So I have ln of 2 on the left side, and that's equal to ln of e to whatever my exponent is that exponent. So ln of e to the 0.08t will be 0.08t. So I got 0.08t equaling to the natural log of 2. And now to solve for t, we divide both sides by 0.08. So this will be t. And in this case, in the calculator we'll press the ln key and then 2, close the parentheses around the 2, because you only want the natural log of 2. Whatever that is will be divided by 0.08. Then hit enter. Let's see, the one decimal place, this will be approximately 8.7. So what that means here is this. It's going to take 8.7 years for a $8,000 investment to double at 8% compounded continuously. And finally, example 10. We want to know how long will it take for an investment of $17,425 to reach $25,000 at an interest rate of 4.25% compounded continuously. And you want to round your answer to one decimal place. Let's identify what we have. We have a $17,425 investment. That's your P. And then we wanted to grow to $25,000. That's your A. The interest rate. Here's 4.25%. Now 4.25% as a decimal. Here's 4.25 divided by 100. That'd be 0.0425. And it does say compounded continuously. So like In that last example, we're going to use this formula. A is equal to P times e to the RT. A is equal to P times e to the RT. So now we substitute into this formula. Your A is going to be $25,000. That's equal to P, which is $17,425 times e to the R, that's the 0.0425 times t. So now we need to get that exponential part by itself. We're multiplying it by 17,425, so we need to divide both sides by 17,425. All right, now I know I got e to the 0.0425 t. And I'm going to leave that 25,000 over 17,425 as is. Because I'm going to try to get an exact value for t. And of course, e and ln are inverses of each other. So I'm going to take the natural log on both sides of this equation. So this will be ln of 25,000 over 17,425. Then that's equal to ln of e to the 0.0425 t. Now here, ln and e are inverses. So ln of e to whatever your exponent is going to be that exponent, 0.0425 t in this case. And this will be ln of 25,000 over 17,425. And then to solve for t, I'm multiplying it by 0.0425. So I'm going to need to divide both sides by 0.0425. So here t is going to be equal to all of this. That's my exact value. But here I want the approximate value to one decimal place. So here's how I'm going to enter that in the calculator. Let me move this over. Here we go. I'll clear this out. Sorry. Here we go. ln. Type in 25,000 divided by 17,425. Close parentheses. And then that's going to be divided by 0.0425. Hit enter. And to one decimal place, this will be approximately, let's say, 8.5. So it's going to take approximately 8.5 years for a $17,425 investment to grow to $25,000 at 4.25% compounded continuously. Okay. So that's what we use to help us find the amount of time it's going to take for an investment to reach a certain amount at a given interest rate. And it could be compounded continuously, or it could be compounded semi-annually, or monthly, or daily, or quarterly. Okay, so that will complete this video on section 4.4, which is exponential and logarithmic equations. That homework will be available for you to complete. for that section. Also, do feel free to email me or just email me if you have any questions or any concerns about the homework. Okay. Thank you very much.